Hello all of my wonderful cyber calculus students. This is Mr. Meyring. This is another video here working with our Q theory, our second lesson on it. Unfortunately, I'm not able to be in class today, so hopefully this is enough for you to learn what you need. We're just going to look at two things today, the expected wait time and the expected number of people in the system. So this is a pickup of our Q theory work where we've already talked about the probability of having a certain amount of people in line, and that's going to be important today for us, of course, because we're talking about expected values. Now, in this work, I do warn you that there are a lot of proofs and there are a lot of steps. So I do recommend that you pause when you need to in order to copy down the work that I'm doing so that you can listen to the explanations and make better sense of it. So feel free to do that. That's why it's a video, and so hopefully that it will help. We start, of course, with working on the expected number of people in the system. Now, again, we talked before about the probability that there are n people in the system at a given time. That's, of course, once the system has reached its steady state, the equilibrium. So we talked about that before, and that the probability of having n people in it is given by lambda over mu. Again, lambda is your arrival rate, mu is your service rate. So lambda over mu to the n, all times mu minus lambda, all divided by mu. And what we're going to do here for our calculations is do a little substitution. We're going to let this Greek letter rho, R-H-O, it's a lowercase p, we're going to let that Greek letter equal lambda over mu, because then I don't have to deal with fractions so much. It'll just make it a little bit easier. And so if you do your algebra on this probability expression here, your probability of having n people in it becomes rho to the n, because that's been substituted, all times 1 minus rho. That will be what your probability of having n people in the system is. So as we go to actually looking at the proof of this, how to actually look at this expected number of people in the system, we go to the pen and paper. We're going to call that expected number of people in the system, we're going to call that L. So L is an expected value of how many people there are. So that's going to be the sum of all the different number or lengths of lines we could have, rather, and J is going to represent the number of people in the system still, and that has to be multiplied by the probability that you are actually in that state. So P sub J, I guess this should be down here instead. But so it's the sum of all of your different line lengths, and of course we can have anywhere from 0 people in line all the way to infinity people in line. That is our assumption. So that is our basic setup of the expected value. Same expected value that we've done before. Number of people times the probability of having all those people, multiply them, and add up all those different possibilities, and that ends up being your average. Well, we are going to have to manipulate this a little bit. And so as I look at what we can do with this P sub J, we can use what we have up here. And so this equals the sum from 0 to infinity of J times rho to the J, all times 1 minus rho. So I just did that substitution. These are your Greek letter rho. There, the lambda over mu that we talked about already. Now as I look at this, I can take a look and say, all right, well, this is a summation. And a summation is something that should be familiar to us. It's working with all of the j's. And as I look at my expression that I'm supposed to be summing, I notice that I have this 1 minus rho. That does not have any j's in it. So I can pull that all the way out front. What I'm working towards here is trying to simplify this summation into something we're more familiar with. And I forgot to write that out front, so I guess I'll just write it all again. So like I said, what we're going to do is take this and put it all the way out front. So here we go. 1 minus rho, all times the sum from J equals 0 to infinity of J times rho to the J. Just enough room there. And so this step isn't really necessary. I forgot to take that out. And so we take out the 1 minus rho because it doesn't have anything to do with this summation. All right? Well, now I want to work with this a little bit to make it more familiar. We're going to do a little bit of trick here. I already pulled out a 1 minus row. I see I have a row here. I'm going to pull out another one, and we'll see why in a second. So I pull out an extra row, and I still have 1 minus row out front. Still have the summation, j equals 0 to infinity. I still have a j, but now it's times row, and if I factored one row out, this is then row to the j minus 1. And that's exactly where the trick comes in. Because if I look at just this part right there in parentheses, if I look at this, this might be familiar to us. If this was an x and that was an n, you might say that this is the derivative. And so that's exactly the trick here. This expression is actually a derivative expression. So as I rewrite, everything out front stays the same. You still have the summation. But now I'm going to write this a little bit differently. This is the derivative with respect to rho, because that is going to be what I consider my variable, of rho to the j. Because if I did do my derivative, if I was going this direction, you would bring down your power and subtract 1 from the power, which is exactly what we have here. And so we end up with it that way. And now we can go further. We have a rho times 1 minus rho out front. I can go a little bit further with this, because if I have the sum of my derivatives, right, if I do the sum of however many terms there are, because I mean, this is an infinite sum, so there are infinite terms being added together, and then apparently I'm doing the derivative of each one of them. Well, that would be the same thing as doing the derivative of the sum, right? Because you know that you can do the derivative of just one part, or you can do each part individually. And so I can write it like this instead, where I want to do the derivative of the sum. It means the same thing. Well, if I look at this, if I look at that statement right there, if we recognize that, that is hopefully what you recognize as a series, where you have rho to the 0, plus rho to the first, plus rho to the second, plus so on and so forth, plus rho to the n, and forever. And we should recognize this as a geometric series. And of course, we know that this series should converge because we already know that rho is lambda over mu, and what we talked about before was that lambda over mu is going to be less than 1. And so this, your initial term, is going to equal 1, where our multiplier, r, is going to be rho. And so this expression can converge because it is a geometric series with these things stated. And so we continue writing rho times 1 minus rho. I am doing the derivative with respect to rho still, but it is the derivative of the convergence of this, because I know this does converge as it is a series. This converges to 1 times, because that's my initial multiplier, so I'll leave that out, 1 over 1 minus rho. That's a lot better, because now I don't have this infinite sum in here, and I can try to work towards finding out just one expression. I can figure out what the derivative of this is, hopefully pretty easy, rho times 1 minus rho, and I do the derivative of 1 over 1 minus, with respect to rho, of course, and so you have a negative 1 from the derivative of the denominator times by a negative 1 minus rho to the negative 2. That should be familiar from your derivatives. If you can't see how that connection is, rewrite this as 1 minus rho all to the negative first, and you will end up with this as your derivative. And so this, I'll simplify down on here. This becomes rho times 1 minus rho. These negatives cancel each other out, of course, times, bring it back to your denominator, 1 minus rho quantity squared in the denominator. And that's pretty nice. That cancels with this, and this equals rho over 1 minus rho. And this is now going to be your expected value, simplified as far as it can get. Now, we did a substitution here we get down to this fact where L, which is our expected number of people in the system, equals rho over 1 minus rho. In your work, when you're actually using this stuff, you probably don't want to be using rows. And so as we substitute back in our lambda over mu, you end up with lambda over mu all over 1 minus lambda over mu, which if you do your common denominator work in the denominator and cancel some stuff out, that all boils down to lambda over mu minus lambda. So that is a nice, easy way for us to figure out the expected number of people in the system. We noticed the other day that our probability work runs down to just lambda and mu and some relationship of those as well. And so it's really nice here again that the expected number of people in the system. So this is on average, if we're in a steady state in equilibrium, everything's running smoothly, on average, this expression is going to give us how many people are actually in that system at that time. So just to summarize then, the expected number of people in the system, we'll call that L, is rho over 1 minus rho. And if you do your simplification to it, put it back in terms of lambda and mu, that's what you end up with. So that is something that we can use to determine how many people we expect to have in the system. We move on. We move on to the expected wait time. So if you're in the system, how long do you expect to be there? And we're going to let W be that expected wait time. And so we'll go over and take a look at this. If we let W be that expected wait time, I'm going to try to draw this with a diagram. So we draw a diagram here. Let's say this is our initial line, you know, that you're actually standing in. Imagine you standing in the lunch line. Then you get to this point and you go over here. This is where your service is. So you have your line and you have the service. Just a simple general aid, general visual aid. So we have the start and we have our finish here. All right, well, we're looking for W. How much time does it take me to get through this? And so if you come in here and you start at the very end of the line. You know, this system is in a equilibrium. It's in a steady state. So you're going to start at the very beginning of the line. You move on down the line. You wait just like everybody else. And you end up getting down to the very beginning, or the end of the line, I guess, and you start your service. So now you're getting your service, however long that takes, and you finish. And then you go off and do whatever you need to do. So this is you waiting in line. Okay, well that's W. W is your expected wait time because we're in a steady state. So however long it took you to go through this system is W. Well, once you leave, you go off and do whatever. You turn around and you look and you say, well, wait a minute, there's still all these people in line. Because, of course, we're in an equilibrium. As you go through a line, more people come behind you and are waiting in line behind you this entire time. And so you are waiting, and then as you move up, people are waiting behind you. Well, they have to wait that expected time as well. As soon as you finish, if you turn and look and take a look at all these people, you could count those number of people. And that would be the number of people in line. Well, if this is the expected wait time and we're in an equilibrium, we know how many people are in line. That is going to be L, which we just figured out. L is the number of people in line on average, the expected value. We also know lambda. Lambda is the rate of arrivals, or arrival rate. So if I look at this and I say, well, if I finish and I turn and look, say, well, I see that there are L people in line, that has to equal lambda, the rate at which they arrive, times how long I was in line, because there's that many people in it. L equals lambda times W. Well, this is an easy way for us to solve for W then, the expected wait time in the system. W is going to equal L divided by lambda, and we just got done figuring out what L is. L is going to be lambda divided by mu minus lambda, and we're going to multiply by 1 over lambda to allow us to divide by it. And that's pretty nice because this lambda and that lambda cancel. And W, your expected wait time, is 1 over mu minus lambda. So again, you are in line and in service, so you are in the system for a certain amount of time. We call that W because it's a steady state equilibrium. You turn and look, you see that there are L people in line. You know how long you were in line. You know the lambda is how fast they arrive, so that's what you end up with. And so as we go back, you arrive in the system, stand in line, get served. When you leave, there should be, on average, L people in the system. Whoever is in the system arrived while you were waiting, which is on average W. So L equals lambda times W. And you end up getting to this point where W equals 1 over mu minus lambda. That is your expected wait time. Once again, boils down to just lambda and mu. So in summary then, this is all the important stuff that you need to know. Your arrival rate, your service rate, average number of customers in the system, average time a customer spends in the system, that's W, and then average time a customer spends in service is 1 over mu. So here you have your final summary of all the important units you will need. Make sure you write these down and have them somewhere that you can use when you end up doing your project. So thank you very much for listening. Remember to go back to listen to whatever you need if there's anything that's not making sense.